there are many dimples in the golf balls, and that they have various patterns and various depths to those dimples. What we found is that each manufacturer has their own theory on the number of dimples, the dimple depths, and the patterns at which they're arranged. We also found that dimples usually go between 250 to 500 per golf ball, but the ideal golf ball has between 380 and 432 dimples. This optimum number of dimples also depends on the golfer and his swing. Every manufacturer, again, has their own theory on the pattern of dimples on the golf ball. What we found with the patterns is that it's more of an art than a science, and so far it's been more trial and error than anything else to figure out which is the best type of dimple pattern. Up to now, dimple design has been more of an art than a science, and for many years, sporting good companies would design their dimple patterns and depths by simple trial and error, testing prototypes and prototype against one another. The new study takes a different approach, asking how to design dimple size and pattern based on mathematical equations that model the physics of the golf ball in flight. Working out the solution to these equations, even on the fastest personal computers today, is not feasible since it would take more than 15 years of computing time just to get a glimpse of the flow around a golf ball for a fraction of a second. This YouTube video shows some of what we found.
You are flying next to a golf ball, sailing through the sky. It's long been known that pocking a golf ball with small dimples lessens the effect of air drag as it travels. But precisely how this happens has never been quantitatively understood. Now, researchers from Arizona State University and the University of Maryland have visualized the airflow with a supercomputer, moving into about 45 degrees from the leading surface of the ball. We can see a number of trains of vortices have developed. These lines of whirlpools follow the scallops of the dimples in the direction of the airstream. Closing in now on the air's behavior around just a pair of dimples, we see the airflow evolve from front to back. Watch now within a single dimple as the air detaches and shears away, varying with the stream's direction. We see that the cumulative effect of the vortices pulls air down onto the ball, delaying energy-wasting separation. Golf balls with dimples turn out to be almost twice as slippery as those without. But how many dimples should there be? How deep? What shape? Since there are no rules regulating these factors, sporting goods companies are free to tee up new patterns. But detailed numerical visual analysis, like we see here, will no doubt play a big part in golf ball design from now on. For LiveScience.com, I'm Dave Brody.
Our hypothesis was that dimpled balls will have increased flight time, and our hypothesis was that dimpled balls will have increased flight time and distance due to reduced drag. Smooth surface would equal a laminar flow, and a dimpled surface would equal a turbulent flow. We have some assumptions. One is that there's no wind. Two, there's no change in air conditions due to altitude or humidity. And three is there's no spin.
Now we will look at the analysis and explanation of our project. We found it best to explain this phenomena by looking at the smooth and dimpled golf balls. First, we'll look at the dynamics behind a smooth golf ball. When a golf ball is in flight, it experiences resistance due to the air molecules in contact with it. Air that slides past the ball close to its surface is called the boundary layer. Air molecules pass the golf ball parallel to its surface, creating laminar flow. This laminar flow on the smooth golf ball creates a low pressure zone behind the ball, and this low pressure zone, also known as drag, decelerates the ball. When we're looking at the dynamics behind a dimpled golf ball, we see that as the golf ball is in flight, the dimples cause the air flowing around the ball to become turbulent and to stay closer to the ball's surface. This turbulence causes the air to hug the surface of the golf ball closer, and and since it's hugging the golf ball closer, it creates a smaller area of the low pressure zone behind the golf ball. And you can see this difference in the picture, demonstrating the smooth and the dimpled golf ball, that the low pressure zone is greater behind the smooth golf ball than it is behind the dimpled golf ball. Since this low pressure area is smaller behind the dimpled golf ball, it creates less drag and allows the golf ball to travel further and be in the air for a longer amount of time.
Conclusion: a dimpled ball travels further than a smooth ball due to the reduction in drag on the ball. The turbulent flow produced by the dimples present on the golf ball reduces the drag experienced by the ball, allowing it to have a longer flight time and travel a further distance. Thank you.